All right, I'll just jump right in here because we're getting a little late start. I'm sorry again. It's Thursday, right? Happy Thursday. Let me fire up project. We're going to talk about project 1, our checkers solver here. See if we can't come up with a solution. If we've got time, I think we'll probably have time. We can get into the next project, but if not, we can wait just a little bit on that. So we've got, take a look at our schedule. We want 2 weeks for that one. So if we do that one, we started on the 14th. I don't want it to be due the same day as the midterm. So I think if we talk about the next project on the 14th, then we can have it due after break. I mean, you can get it done before. Is that bad to have a project over break? Okay. Because again, I can't see anything here. There we go. Let me pull up chat. Forgot. No, you'll have time on it. You should have time during the midterm week because it's not going to be super intense or anything. But try not to pile up a due date and that. But so if you want to use your time to get it done, it should be okay. If not, you've got a little bit of wiggle time there. So let's plan to talk about that one on the 14th, and then we do on the 7th, and that should work out pretty well. Back to my friend. Thank you so much for donating those bits. You are such a legend, sir. Supports the Student Scholarship Fund here at the University of Michigan Dearborn College of Engineering and Computer Science. We're coming close due to another donation. That's awesome. All right, so we start up a new project for project 1, checkers. So a couple things with this, right? We were going to make our solver class here that accepts a 2D list to the board, right? Our init method should accept the board. So I can give it any checkerboard to solve. We need to make sure it's valid, right? All the pieces are either on white squares or black squares, or raise an exception here. And then our get max jumps will return the max number of jumps for any white checker. So for every piece, we need to do this recursive backtracking to see, hey, how many jumps can I go? All right, so we can have our class for checkers solver or something, whatever we want to call it here is probably fine. And we'll define an init method. Oops, init define. It had it. There it goes, init. So init needs to take a board, right? So here's the checkers board. So we can have our self board equal the board. And again, if it's private is better. We don't want people messing with the board directly. If it's public, again, not the worst thing in the world here, but we want to be in the habit of making our values private here. So we got our board, and then we need to validate the board. So a couple different approaches for that. Either we look at row numbers and column numbers, and so they will all be alternating odd, even, odd, even, odd, even, odd, even for pieces, right? So if all your pieces are on odd columns in the first row, all the pieces in the next row need to be on even columns, right, to get that diagonal in. I think that's probably the easiest approach here. So we're going to find the first checker, see if it's odd or even, and then look at all the rest of them and make sure that they do follow that alternating pattern here. So we can say for index, I guess we can even make sure the board is an 8x8 as well too. So say if the length of the board not equal 8, there we go. We can raise a value error and say invalid board size or something. I mean, the same idea should work no matter what length of board we use, but if we want to make sure it is an 8x8 board, that's probably perfectly fine here. And then we can even check, for row in board, if the length of the row does not equal 8, again, raise this one here. Not super concerned if you did the 8x8 checking here, but this is a quick way for us to do it. Now we can go through it and make sure all the pieces are in the right spot. This was the important part, make sure our pieces are in the right spot. So for row in, now if we're doing indexes, right, we don't really care about the row number, we care about the column number. So I can loop through for row in board here, going one row at a time, right? And then each row, now I need to get the indexes though. So I need to say for column index in the range of the length of the board, range of the row, right? Length of the row here. Now this is where it's going to be important. And now we need to know, should we be looking for evens or odds? Right? Because this is just going to toggle back and forth. So it works out easily to use a Boolean value if you want here. And there's lots of different approaches for this too. This is just one approach here that I think is relatively straightforward, but lots of different ways we could have gone about it here. So we're going to say should be odd. I don't know, what we started as true. I don't think this one really matters what we started as. but we're going to go based on the first one we find, set this to true or false. And then we'll look at the next row and look at if they should be odd or not, to look at our pieces here, this sort of thing. So as we go for each row, for each column in that row, we want to find the first piece. So we're going to say if the row at the column index, right, because this is a list of lists, so each row is a list, we can get at things by index. So for row at the column index does not equal a space. Right, this idea we had spaces for empty spaces, white and black. It's pretty straightforward what it is, but I don't care if it's a white piece or a black piece. Right? Either piece is valid. So if it's not a space, then right for the first one, we want to set. Maybe this should actually start as null here. Maybe we want to start or none. I'll start at the top as none because this is going to be important whether or not we've seen one. So we can say if should be odd is none, then should be odd is going to equal my column index. Now 0 I think we count as even, right? So column index mod 2 will give me 0 for all the evens, right? And 0 is false. It'll give me 1 for all the odd numbers, and 1 is true. So this is sort of a silly Python shortcut here, but so even numbers will be 0, which is false. Is that a useful little, it's kind of a cute little Python trick, right? Because everything is true or false, right? And then odd numbers will be 1, which is true. So this should be the first one we find. Right? If it's none, we're going to set it to true or false. Right? Then elif, right? If it's not none, if should be odd is true, then if this is also not odd, or if this is odd, we're okay. If it's not odd, we have a problem because it should be odd. So it gets maybe it's a little funky. I thought this was kind of straightforward, but just kind of thinking through. So if we know this row should have pieces on the odd columns, right? Should be odd, should be true. Then we can check. Hey, if my column index mod 2, right, is false here, so either not this, or we can say if it equals false. Either way works for us here. We're going to raise value error and say invalid board setup, right? Yeah, okay. It's suggesting what does it want me to do? Comparisons. Oh, is false. There we go. Is false instead of an equal sign. So if the column index is an even number, right, with this mod 2 thing, if it's even, but it should be odd, we'll raise the value error. The other case, though, if it should be odd is false, so if should be odd is not true, this doesn't run, right? And either it is none, it is set to true, or the else here is it's set to false. Then if this is true, I'm going to raise the value error and say it's invalid because it should be even at this point. Right? This means so this else case is should be even or should be not odd. I don't know if that makes sense here. Right? So this is an even number, and these are odd numbers. Number index, even number index. Right, so just sort of using the truthy part of Python to say, hey, if this is true or false. And again, you can have different ifs, so you can say if it equals 0 or if it equals 1, that's perfectly fine as well. On any of those would work. So I think this is good for now, but then the next thing that needs to happen, right, after we've looked at every column index for this row, now we need to flip should be odd, right? So should be odd is going to get flipped, it'll equal not should be odd. Right? Just flip it, make it the opposite, and now we go to the next row. Although that won't work if it's none. Oh dear. Okay, so if should be odd is not none, right? Because if there are no pieces on that first row, it's still going to be none, and that's okay. That's valid. So if should be odd is not none, then we'll flip it. If it is none, we leave it alone. We go to the next row, and we keep on looking. Is it none? Is it should be odd? Oh, is it? That's not going to. It is none. Yeah, no, this is good because we're only triggering it if it's not a space. I think this will work. And we'll try it and see, right? We can give it different boards and see if it works for us. That's sort of what we want to do here. So we could write unit tests. It's probably the right way to do it, right? So we'll go, do we ever look at how to test with exceptions? I don't think we did that, did we? Okay. We can do that another time. We can do it another time. It takes it's not too bad. We'll do it. I'm going to change my mind here. So let's go to test. Create a new test for test. So from main import checker solver, and then we need a function here. So we have a test init invalid board test init invalid board. So we're going to arrange, we're going to act, we're going to assert. So, and let me actually, I can never remember this. So Python unit test for exception. That's what we have to do. Assert raises. I think that's what it is. Assert raises. So assert raises says, what exception do you expect to get from what function? Remember way back last semester, we said you can technically pass a function to another function. And I think we did it with like, it made smiley faces or something. So we'll say, when I use this function, it should raise this exception. So to arrange, then we need our board. Right? So our board will equal a 2D list. So we'll make a list of lists, and we'll have a bunch of spaces. 1, 2, 3, 4, 5, 6, 7, 8. And we'll do this 8 times, and then we can fill in some checkers. 2, 3, 4, 5, 6, 7, 8. And again, we should be checking some of these other ones. Setup, I guess. Make sure it checks on the different row lengths and sizes, but we'll get to those after. I want to do this board first. So if I put a white checker here and then a black checker here, that should be invalid. It's a pretty quick check, I think. So make sure we're not getting that first row. Make sure we're handling that right, because I probably had screwed that up initially. And then we'll find one on the odd numbered columns, right? Because this is 0, 0 is even, so should be odd. And then another odd one on the next row should trigger that this is invalid here. So there is no act here because it's all happening in the assert the way that works. So we're going to say assert raises here a value error. And what does that is calling checker solver given the board. That might not work actually. Shoot, maybe that's why we can use assert raises. Assert raises with assert raises. Okay, maybe this might be the right one. Text with assert raises. String. Okay, let me try that. So I think we want that one. So we'll say with assert raises. Self-assert.raises. Self.assert raises. Value error adds error. Then we can call this function here. And I think that works better. Value error. Oh. Value error adds error. And then what's cool with this, I think you can even check error as well. But this way, because we're passing the argument here, it wasn't going to work well as the definition. I think this is going to be happier. Let's try it. See what happens. Hey, it passed. So if we fix it here, let's make sure it works with the valid board and doesn't raise an error. Now it says value error was not raised. Awesome. So cool. So that worked out well for us here. So we got the value error as we expected. And then you can even check, you can say self.assert equal was it invalid board setup and the error dot exception. I think it's error exception. Is that what they said? Yeah, error exception as a string. Maybe. Let's try this one. Yeah, okay. So you can even check the specific message, which is really cool, right? Because we have board setup versus other things. So, so if we have like 7 rows instead of 8 rows, we should get a different error. Oh dear. Invalid board setup. No, that should have been board size. Well, that's unfortunate. Really? Is this not 1, 2, 3, 4, 5, 6, 7? I'm super confused now. Oh, maybe this is, maybe that goes outside. There, okay. See, it's good to test. You test your tests. So invalid board setup is not invalid board size. So we want the string of this, I think. Is that? Because we don't want the value error message there too, do we? Yeah, there we go. Expected and actual. Now if we uncomment this back out, run it again. Oh dear. Uh-oh. Oh, capital I. Okay, I was worried I messed that up. So capital I, invalid board setup. Lowercase I. And a pass. That was totally worth it, right? Okay, so seems to be validating. Awesome. Next up, get max jumps. Get max jumps. So for get max jumps, we want this to be the public function here, right? We're still going to use recursive backtracking, but we don't need get max jumps to be the one that is the recursive backtracking function, because we probably need some additional pieces of information here, right? So eventually this will return some sort of value here, but what we want to do is use a private helper function, get max jumps, and then probably tell it a location, right? Maybe a row index and a column index, and a column index. It's similar to how we were moving along and following, hey, this is where the particular maze move is, right? When we were solving the maze. So this one can call this one. And so really we want to say for row in self board. And then actually, so we need the row index, oh bummer. So we need the row index. So we need for row index in range of the length of self board, right? And then for column index in the range of the length of the self.board at the row index, because we want to be particular here. They should match because we made sure it's a square, but again, it's just better habit here. We'll say, hey, if my self.board at the row index at, oh, self underscore board, there we go. I was going to get that wrong. There is no board, self underscore board. Board row index at the column index is equal to a white checker. And now using these like strings here is probably improper. It'd be better here if we said, hey, this is white, right? And then we had black, right? Is B, and then empty maybe as just a space. Just to be consistent, then we can have names here, right? Rather than just a W everywhere. This can now can be self.white, right? If it's a white checker. If it is, we got to call get max jumps. So we need eventually to get the maximum number of jumps here. So I might, one option here is might have a list. So I'm going to have a list of jump lengths, maybe. Jump lengths. Start as a list. And we can take my jump lengths, and we can append whatever we get back from self.get max jumps given the row index and the column index. Right? We can track that. Sure. Right? We can just append it. So this will trigger the recursive piece. This one will just try every white checker. And eventually when we're done, if this worked out right, we can return the max of jump lengths. Might be 0. I guess if a board would still be valid if it had no white checkers, and then there'd be nothing in here. So we should return 0 if there's no white checkers, I guess. If length of jump lengths is equal to 0, return 0. That, you probably didn't run into this. That's probably a weird edge case. Why would you give it a checkerboard with no white checkers? Because that's probably invalid too, but I just thought of that. Right, so our get max jumps then for a given row and column. Now, we need a place to be tracking how many jumps we've currently gone, so that every time this function gets called, we can track that. We can either pass it in here as an argument to track that at the function level, or we can have a class level variable for it. Either way is okay. So with the maze solver, we have that class level variable that said, hey, this was my current number of steps, right? We could do that. It's perfectly fine. The only problem is we need to reset it each time. And that could be okay. So maybe we add a self dot current jumps is 0. And then what we want to do is every time before we call self get max jumps, reset that back to 0. Because that way, the next time I find a white checker, I'm going to put current jumps back to 0. Actually, the unwinding will even probably take care of that too, won't it? Probably don't even need that. Let's see. So as we're doing our max jumps, so pretty quick, right? We're going to see, can I go this direction, or can I go this direction, or can I go this direction, or can I go this direction, right? So if self dot can jump, and then what my row index, so -2, column index -2 is up 2, left 2. Right? So if we can jump there, then we'll jump there. So we'll take my self dot current jumps, add 1 to it. So say I jumped, right? And then we need to change the board. So we'll take our self dot board at the row index, at the column index, add self dot blank or empty, right? We're moving the white checker. Take the white checker off of where it currently is. Then if we can jump that direction, I board at the row index -1, at the column index -1. That's where the black checker we're jumping over is. Also needs to go to empty, right? And then where we're landing, we need to put ourselves. So -2, -2, we put the white checker back down. Right, so we're changing the board here. Then we're going to recurse. We're going to call self get max jumps at this new location. Get max jumps, no, private. Get max jumps at the row index -2, column index -2. Right, this will recurse. Whenever this is done here, we've gotten as far as we can, right? We've gotten, and there's no more steps we can do. We need to undo, right? So we're going to just do this in reverse. And if you like it actually in reverse, like I do, just that makes me happy. I do it this way. The order doesn't technically matter here, but I like that it's more symmetrical this way. It just makes me happy. We just undo all these steps. So once we're done, we need to undo these changes that we did. So this is now empty again. This is now a black checker again. And now this is now a white checker again. And then we uncount that jump, because maybe now we're going to try the other path. Right? So if we can jump, great. Okay, then we'll check the other direction. And really all of this now stays the same except for +1 and or -1, -2 sort of things. So if the only thing that's different is the numbers here, we could turn this into its own function, right? So maybe we call this try jump, given a row modifier and a column modifier. Does that make sense? And instead of +2 and -2, oh wait, I guess we still need the row index and the row index and the column index. But if you give it the modifier now, I can subtract. Actually, I'm going to add the modifier here, which is a little funny, but that way I can pass it negatives plus the column modifier, right? So we can say, hey, this is -2, -2, or +2, +2, or -2, +2, whatever that combination is here. And then this will be plus that divided by 2, and plus that divided by 2. Again, just a kind of a silly optimization here, but it works out pretty nice here because we don't have to call the same code more than once. Column modifier plus the row modifier plus the column modifier plus the row modifier plus the column modifier plus the row modifier divided by 2, right? Because this is the black one we're jumping over, plus the column modifier divided by 2. We reset original back to white, take our current jumps down. So try to jump here. So we're going to say self dot try to jump, given the row index, the column index, and then -2, -2. Right, so this is up left, right? And then we have up right. is going to increase our column by 2, still row goes down, and then a down left is plus 2 rows, minus 2 columns, and then a down right is going to be plus 2, right? Add 2 rows, add 2 columns. That's going to try and jump all those different directions here. And it's only going to do it if we can jump, so we still have to add the can jump here. So define a self.can jump given a row index. Oh, that's not. So we also need the row index here too. Bummer. We need row index and column index. And then we need the modifiers, right? Or this is where we're going to land, I guess. I think we just give it the modifiers. That'll work. We'll just give it the modifiers. So this needs row index. Oh, self. My goodness, I can't type here. Define can jump. Given self, row index, column index, row modifier, and column modifier. All right. So first you need to make sure that these are going to be in bounds. So if my row index plus the row modifier, right, this is not, right, between greater than or equal to 0, less than length of self board. Right, this is valid here, right? And same with the column index, right? So 0 less than or equal to column index plus the column modifier less than the length of self.board at the row index, right? So if those are good, then I know where I'm trying to get is a valid space, right? If that's a valid space, then I need to check if the self.board at the row index plus the row modifier divided by 2 is equal to self.black. And the column index plus the column modifier divided by 2. Right? Is there a black piece to jump over at that location? Right? If that's good, then this is and here, and where I'm going to land is empty. Self.board at the row index plus the row modifier at the column index plus the column modifier is equal to self.empty. So am I going to land in bounds? Am I jumping over a black piece? And is the space empty that I'm going to land in? Yeah, if all that's true, I just return that. I can just say, here's a big statement. This is either true or false here. Right? Now what's great with anding together here, if this is false, because Python knows it's anding, the whole thing will be false. I'm never going to get an index out of bounds exception sort of error here, because that's okay. We're not going to run into issues where I'm out of bounds, because this is already going to be false. So if we can jump, right, then we'll go and jump here. So we're going to try to do all these jumps here. But as we're trying to jump, right, we need to be tracking the furthest that we got. So we probably also need a place to track our current max jumps. So current max jumps starts at 0. So this is the one that we're going to have to change every time here. So this will be important. We can reset this one every white piece. But what get max jumps is going to do, we can say, hey, if my self.current jumps, is greater than my self.current max jumps, self.current max jumps is equal to my self.current jumps. Right? We need to be tracking this. If I've gotten farther than I've gotten before, I have a new max. Then let's try all these things. These will recursively call get max jumps if I can go that location. Right? So with this test board we had, that's a bad one here. We need another one. So let's test get max jumps. Test get max jumps. here. So if we just have white piece, a black piece, empty, a black piece there, black piece there. Let's do one more over here and a black piece here, right? I should be able to go one jump, two jumps, three jumps this way, and one jump, two jumps this way. So it should be three, right? So there's no assert equals here. We will arrange here. So my checkers solver is checker solver given the board. And then we can assert, or we get the actual max jumps. Well, max jumps. Checker solver.get max jumps. And that should be my expected max jumps. Expected max jumps was 3, we said, right? Equals 3. There we go. So my expected and the actual. Right? 1, 2, 3. Should do that. So as we're going, right? Once I find the white checker, we're going to make sure that starts at 0, because if I have more than one white checker, we want to make sure we start that checker's current max jumps at 0. Eventually that'll get added. Then we'll call get max jumps. We'll see, have I gotten further? And then we'll try. If nothing happens, we don't do it. If nothing happens, we don't do it. Down left, nothing. Down right should work. So down right should trigger this one to try jump. We can jump, should be true. We'll add a jump. We'll move the checker, right? Remove the black piece, put the checker in, recurse. When we get back to get max jumps, right? We're now at a different location. The sort of thing we just keep on going over and over and over here. So let's see if it works. Oh, what did we get here? List indices must be integers or slices, not floats. Oh, when I divide it by 2, I want integer division, right? No. The modifier 2 divided by 2, probably just because we're doing division. I think we can get away with integer division. Because it should always be 2 or negative 2. It should always give me 1. Let's try that. Nope. Okay, well now we got expected 3, actual none. Oh, what happened here? We never returned anything, did we? So our get max jumps should return actually none. Oh, get max jumps didn't return anything. That's the problem. So when get max jumps is done, if we're not adding that to the list, right? Because this one never is going to return because it doesn't know what is the max. Okay, so let's make this one a self dot variable here. We can track this. So self dot jump lengths here is an empty list. Then we'll say, hey, if we have a new max, we'll take our self dot jump lengths. We can append self dot current jumps. Current jumps or current max, they're the same value here, right? We'll append it. So we're going to get a lot more values in here than we need. But when we're done, we should still be able to return the right max one here. Self dot jump lengths. So I'm not going to get the jump length for each single checker. I'm just going to get a lot of different jump lengths in there, but that's probably okay. There's probably ways we could do it, but I think that'll give me a 3 now. No? Uh-oh. Greater than is not supported in instances of none type and int. Where? None type and int. How did I? Oh, we don't need to append here because we're already doing that. That's already happening. So we're adding a bunch of nuns. Sorry. Let's try it again. Hey, we got 3. That was super exciting. I'm super excited. So let's put another checker in. So if I have another checker, say over where? Where should we put another checker? If I put one over here, a white checker and a black checker here. That one should be able to go 1, 2, 3 as well. or 1, 2. This one should still go. So should still be 3 here, okay, with multiple checkers. Let's try that. Still got 3. Okay. Want another path where we can get more than 3 maybe? So maybe we go down here, we'll land here, and then maybe over here. What are we going to get? So this one can go 1, 2, 3, 4, 5. This one can go 1, 2, 3, 4, 5 this way or 5 this way. So it should be 5, I think, at that point. I probably should write multiple tests here instead of just playing with the first one, but you get the idea, right? So we got a 5 out. It looked pretty good. Right? Make sure we don't jump off the board. Probably a good idea too. Yeah, doesn't try and jump off the board. Doesn't error. All right, so how are we doing on 2D list accepts, or init accepts the 2D list for the board, validates it. Check. Get max jumps, calculates max jumps for 1, right checker correctly. I'm assuming it does, right? We tried with 1, and then from all checkers, we added some more. Now they were the same though, right? Do we make sure that if they're different? So let me put another white checker, say like over here. No, where do we want to put it? If I have one over here, it could go 1, 2, 3, 4. Oh, that's still 5. Oh goodness. 1. Where can we put it that it won't have that many jumps? We can go. Oh, with a different number of jumps. Let me throw one in here. Let's get 1, 2, 3. That'll get 1, 2, 3. No, 1, 2. That's all 3 now. Why do they all have the same? Why can't I think of a better checkerboard? All right, I'll make another one here. Let me just totally change the checkerboard. Checkerboard more. I don't know. That's a bad name, but that's okay. So if we have a white checker here, a black checker here, and a space, that'll get 1 jump. Right? Every other? Yeah, now we're every other. And then this one should still be able to get 1, 2, 3, 4, 5. Right? So this checker only gets 1 jump in. This checker should be able to get 5. Right? Just to make sure it's getting it from all of them. Okay. Now I feel better. Feel a little better. Thoughts? Concerns? Anyone in chat? Okay. Probably a little different than yours looked. But again, I know this is an optimization I can take, so I apologize. Maybe that's a little bit cheating here, but if the code is exactly the same for either you +2, -2, you can turn that into an argument here or parameter. So I think this is about as concise as we can get it here. Right, this is the undo step, or that's the change step. That's the undo step. Right, and we just check. If I can jump there, great. So that was checkers. Awesome. I'll go ahead and commit that one. Project 1. All right, so we've got a little bit of time. Oh no, we're waiting on the next project though. And then for linked lists, what we have left to talk about linked lists is to actually make the positional linked list of the book uses. I think we'll save that for lab. It's just an exercise in not even really copy paste, but using it and making sure we can get the positional piece to work, because we'll get some cool performance benefits. So we'll talk about that in lab and look at the performance benefits of the two, and see if maybe we can do some timings or something. So that sound good? All right, awesome. Yeah, I think we can call it a day then. Very cool. I will see you next week. We'll get into new stuff and trees. It'll be a lot of fun. Thanks so much.